For the second part of section 5.4, we're going to look at integration that involves natural exponential functions. The first one's like really simple. So here are our two formulas. The integral of e to the x with respect to x is equal to e to the x plus c. Because e to the x is its own derivative, it's also its own integral. But things get a little trickier if we have integral of e to something other than just x. So for your second formula, we have the integral of e to the u with respect to u. And that will equal e to the u plus c, which looks really a little more simplistic than it is. This means that you must sacrifice the derivative of the exponent before you integrate back to e to the u. And remember that your book calls du your sacrifice. That's that chain rules derivative that has to be sacrificed before you can integrate. So make sure that you take good note on that. So some other things we have to sacrifice the derivative of in order to integrate. If you have parentheses to a power, let's just review that. What do you have to sacrifice to integrate a parentheses to a power?
And what's in the parentheses?
The derivative of the inside. So that's considered your du. If you have a trig function with an angle other than x, what do you have to sacrifice before you can integrate it? The derivative of the angle. So this is a third thing that we have to sacrifice. If we have e to a power other than x, you have to sacrifice the derivative of the power. That becomes your du. So you have to do that before you can integrate back. For this next example, we have the integral of e to the 3x plus 1. Now, we don't have e to the x, we have e to the u. And our u is 3x plus 1. And in order to integrate that, I'm going to need to sacrifice not just a dx, but a what? A 3 dx, right. Because the derivative of my exponent is 3. So I'm going to have to insert a 3 and balance it with a 1/3. This becomes my sacrifice. So that's just the chain rule reversing itself. And that's your u prime getting sucked off of there. Then when you integrate e to the 3x plus 1, it's its own integral as long as you have sacrificed the derivative of the exponent. So that is e to the 1/3 e to the 3x plus 1 plus 8, an unknown constant of c. So that one's not too bad, right? Okay. For the second one, we have the integral of 5x e to the negative x squared. So this one's a little trickier. If I ignore the 5 and the x, if I just look at the e to the negative x squared, because that's the more complicated of the functions. Now remember that there's no product rule for integrals. So, if we can't sacrifice that x, we're in trouble. You can't have a leftover x there. Something has to happen to it. But it turns out that I need to give away a what? A negative 2x. So, I'm going to bring the 5 outside. I'm going to rearrange it to look like this. I'm going to move the x back here with the dx because that's going to become part of my sacrifice. And then I'm also missing a negative 2. And I'm not going to use the 5, so I just booted him outside. So I'm going to make up a negative 2 right here. I'm going to balance it out front with a negative 1/2. So this is what you sacrifice. And once again, remember that when you integrate e to a power, you do not do the power rule. It simply is its own integral once you have sacrificed the derivative of the exponent. So this is my u, this is my du, and then the integral of e to the u du is just itself. So we have negative 5/2 as our coefficient, e to the negative x squared plus c.
Do we move it down for the negative exponent?
Do you move it down?
Because of the negative exponent?
You could. They will let you leave negative exponents on e's but not on x's. So you don't have to, but yeah, you certainly could write it as negative 5 over 2 e to the positive x squared. So those are actually exactly the same thing. Next example. We have the integral of e to the 1 over x all over x squared with respect to x. So the first thing we're going to do is rewrite all of those fractions as negative exponents. So the top becomes e to the x to the negative 1. Remember from a long time ago that 1 over x is written as x to the negative 1 in order to take its derivative. And x squared on bottom becomes x to the negative 2 on top. So we're going to look at it like this. It is e to the u in some ways. And we have to give away the derivative of the exponent. And the derivative of x to the negative 1 is negative 1x to the negative 2, which is great, well, with respect to x, which is great for us because we have the x to the negative 2 and we only have to balance it with a negative 1. So we're going to multiply in a negative 1, let that become part of my du, which is going to be my sacrifice. And we're going to balance it outside with a negative as well. So this is given away, and then since it was an e to a power, it is its own integral, negative e to the x to the negative 1 plus c. And this your book won't let you stop on because negative is on the x, not the e, unlike we talked about before. So this we're going to bring back to the original negative e to the 1 over x plus c. Okay, so if we want to integrate e to the negative x, that's pretty easy. All we need to sacrifice is a negative 1. So we'll make up a negative 1. And that'll become our du right here. And we'll balance it with a negative. We'll give that away. And then our integral will be negative e to the negative x plus c. And they will let you stop there. But if you wanted to, you could rewrite that as negative 1 over e to the positive x plus c. Does not matter at all. Your book does not care if you have negative exponents on your e's, just not on your x's. Is that okay, you guys? All right. This is called what type of integral?
Indefinite.
Indefinite, okay? And indefinite integrals still have variables in their answer, and they have that plus c at the end. Over here, we're going to work the same problem, but we're going to turn it into a definite integral with a lower limit of 0 and an upper limit of 1. So do you all agree that we already know that this integrates to negative e to the negative x?
Mm-hmm.
Okay, because we just did that. So we get that, and then we're going to evaluate it from 0 to 1. I don't know why that dx is sitting there, so let's just take that off. Old habits. Now if I substitute positive 1 in, I get negative e to the negative 1 minus what? Negative e to the negative 0, which is just negative e to the 0. Okay, so there's my substitution. That's my f of b minus f of a. And negative e to the negative 1 can be left. You don't have to change it to negative 1 over e. What is e to the 0? 1. So minus a negative will make a plus 1. So you could stop here. A lot of people don't like to lead with that negative, so we could stop here. Some people go a little crazy, and they go to here. And then some people go even crazier and get a common denominator. I don't know why, I'm just telling you what people do. And they'll multiply this one by e over e. I just want you to be prepared for anything that could happen. But I'm perfectly comfortable with either one of these. But just be aware that in the back of your book sometimes you may see these as your final answer, so I don't want them to scare you.